Welcome to Calculus Conqueror, an introduction to the definition of the derivative. Let's say you are traveling from here to there, and there happens to be 50 miles away from here. It also happens to take you an hour to get from here to there, so clearly your average speed was 50 miles per hour. When we use the word speed, we are talking about a rate of change, namely the rate at which our distance is changing with respect to time. Depicting this on a graph, we have the start of our trip being here, over in the left-hand corner of the graph, and the end of the trip being there, the right-hand corner. And the start of our trip here, we leave at 1 p.m. and at mile marker 50, and an hour later at 2 p.m. we end our trip at mile marker 100. You can dispense with all the words and markings and just put it as with coordinate points, as a graph with coordinate points. So where we start is coordinates 150, 1 being our x value at 1 p.m. and 50 being our y value at the mile marker 50, and the end over on the right is 100. Our average speed is the change in distance over the change in time, which is represented by delta y over delta x, the Greek symbols for d, delta, which represent change mathematically. And our equation for this is y2 minus y1 divided by x2 minus x1, and that is equal to 100 minus 50 divided by 2 minus 1. That equals 50 miles over 1 hour, or, as we said before, simply 50 miles per hour. And 50 miles per hour is actually the algebra slope from here to there. As we can see here, we kind of draw out a triangle, and our change in x is 1 hour from 1 p.m. to 2 p.m., and our change in y is 50 miles, and delta y over delta x is 50 miles per hour. Mathematically, the slope between any 2 points on our graph tells us how fast we were going on average between those 2 points. But how can we tell how fast we are going at any one point in time? Remember, we need 2 points in order to have a slope. So we take what is called the limit of the difference quotient. And the difference quotient is just a fancy phrase for the slope. So slope is represented by m, and that is rise over run, and it's delta y over delta x, which is y2 minus y1 over x2 minus x1. So on our graph, we see the points. The one to the left is x1, y1, and the one to the right is x2, y2. And y2 minus y1 divided by x2 minus x1, when we divide 2 terms, we end up with a quotient. And the phrase, the difference quotient, is the quotient of the differences being y2 minus y1 and x2 minus x1. Sounds like a mouthful, but it's really that simple. Delta y over delta x is the difference quotient. But we're going to change our letters from x1 and y1 to x and f of x, and we're going to change our our x2 and our y2 to x plus h and f of x plus h. So let's take a look at this. Let's take a look at the graph. So what we had before was x1, y1, and now we just simply have x, because we want this x to be at any point along our graph, the x value at any point along our graph. And corresponding to the x value is its function value, or its y value. So we can represent x1, y1 by simply x and f of x. And then if we travel a distance, h, horizontally, to another point, so if we add h to x, our new x point becomes x plus h. And our new y point becomes f of x plus h. So our 2 points, using those 2 points, the difference in our y values is represented by f of x plus h minus f of x, and the difference of our 2 x values, being x and x plus h. If we subtract x from x plus h, we're simply left with h. So our equation for our slope has become delta y over delta x equals f of x plus h minus f of x over h. And that's just a fancy form of saying y2 minus y1 over x2 minus x1, except it's using function notation. And what we're going to do is shrink the distance between these 2 points, x and f of x, and x plus h and f of x plus h. So it's really x1, y1 and x2, y2. We're going to shrink that distance. In other words, h is going to get closer and closer to 0. We look at our graph. As we shrink h to 0, the 2 points get infinitely close to each other. Notice, however, that h cannot equal 0, because if it did, then x plus h, f of x plus h, would simply be x and f of x. And they would be the same point. So h cannot be 0, but it's going to be infinitely close to 0. And mathematically speaking, when we shrink h to 0, that is expressed as the limit as h approaches 0. And it's represented by the limit as h approaches 0. When we take the limit of the difference quotient, we write it as the limit of f of x plus h minus f of x all over h as h approaches 0. This is a fancy way of expressing the slope between any 2 points that are infinitely close to each other. In fact, this is the slope of the tangent line to the curve at any point x, and this slope is represented by dy dx. Looking at our graph again, at the point x, f of x, and we've shrunken h infinitely close to 0, and we've drawn a line tangent to the graph at that point. So in reality, it's really 2 points that are infinitely close to each other. We need 2 points to have a slope, but we're going to pretend that they are so close that it's almost exactly the same as 1 point. And the line tangent to the point is represented by dy dx. That is, now instead of the Greek delta y, we have the Latin dy, which is dy over dx, which is the derivative of y with respect to x, and that is equal to the limit of f of x plus h minus f of x over h as h approaches 0. The slope of the tangent line to the curve is called the derivative, and the definition of the derivative is usually represented by f prime of x, and that's equal to dy dx, the derivative of y with respect to x, which is the limit of f of x plus h minus f of x over h as h approaches 0. The derivative, being the slope of the tangent line, tells you how fast you are going at any point in time. As I said before, in reality, between any 2 points that are infinitely close to each other. The definition of the derivative is our entrance into calculus. So let's take a look at the relationship or a comparison of what we know about algebra and calculus at this point in time. Our algebra slope, m, represents the slope between any 2 points. In calculus, our calculus slope, f prime of x, represents the slope at 1 point. M is equal to delta y over delta x, that is the change in y over the change in x, and that's equal to y2 minus y1 over x2 minus x1. For our calculus slope, f prime of x, which is the derivative of x, is equal to dy dx, being the derivative of y with respect to x. That's equal to the limit of f of x plus h minus f of x all over h as h approaches 0. For our algebra slope, this slope is the average rate of change. And for our calculus slope, the slope is our instantaneous rate of change. So after we take our trip from here to there, we can use the algebra slope to determine our average speed. But during our trip, anytime during our trip, we can use the calculus slope to determine our instantaneous speed. And that's what your speedometer is doing in the car, or whatever vehicle you may have. The next videos will show how we do the math when working with the definition of the derivative. At first we'll do it the algebraic way, and then later we'll do it the calculus way, which turns out to be a lot easier. So this has been an introduction to the definition of the derivative. I hope you've enjoyed, and thank you very much.